What is Voyager 2 actually hearing out there? Right now, more than 13 billion miles from Earth, a spacecraft older than most of the people watching this video is picking up a signal that no human instrument was ever designed to receive from this place. If that single fact does not make you want to see this through to the end, hit subscribe anyway, because what you are about to hear will change the way you picture our solar system. And if you have ever wondered whether NASA is hiding something real from us, this is the story I have been waiting for. Let me start with the real headline, stripped of the noise. On August 4th, 2026, NASA confirmed something almost no one is talking about. A routine engineering maneuver worked. The kind of maneuver that, if it had failed, would have quietly ended a mission older than most of the people reading news articles about it, without anyone outside a small building in Pasadena ever really noticing. It is the kind of news that disappears under louder headlines. But this one matters, because Voyager 2 just bought itself another full year of listening to a place no spacecraft had ever been inside before. That place is the space between the stars. And what Voyager 2 is hearing there has been quietly rewriting our models of the universe for the last several years. Most people do not realize that one of our oldest spacecraft is still teaching us things we cannot learn anywhere else. And the lesson it keeps teaching is that the universe is stranger, louder, and more alive than the textbooks ever let on. To understand why this matters at all, you have to first understand what Voyager 2 is, where it is, and how impossibly far away 13 billion miles really is. Voyager 2 was launched on August 20th, 1977, 17 days before its twin, Voyager 1, which launched on September 5th of that same year. The reason the craft named 2 left first is its trajectory. Voyager 2 was deliberately placed on a slower, longer path, so it could take advantage of a planetary alignment that only happens once every 176 years. A single mission visiting Jupiter, Saturn, Uranus, and Neptune in order. NASA called the route the Grand Tour. Voyager 1 took a faster shortcut through Jupiter and Saturn only, which is why it reached interstellar space years ahead of its sibling. Both spacecraft were originally designed for a 5-year mission. Neither of them has stopped. Voyager 2 is now nearly 49 years into a journey that was supposed to last 5. It visited Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. It remains, to this day, the only spacecraft ever to have flown past the ice giants. Everything we know about those worlds from direct in-person observation comes from a probe built with components older than the people managing its mission. Power has been the defining struggle of the Voyager program for decades. Both probes are powered by radioisotope thermoelectric generators. Plutonium-238 gives off heat as it decays, and that heat is converted directly into electricity. Nuclear batteries in the simplest sense. At launch in 1977, Voyager 2's generator produced around 470 watts. Each year since, as the plutonium has continued to decay, the output has dropped by a small fixed amount until today. After nearly half a century, the entire power budget on the spacecraft is so thin that every single watt has to be argued for. Engineers have been turning things off carefully for years. Heaters first, then backup systems, then science instruments one at a time. Each shutdown is a small funeral. Each one shrinks the list of questions the spacecraft can still answer from its place in the dark. For years now, this has been a slow countdown. The cosmic ray subsystem on Voyager 2 was scheduled to be shut down before the end of 2026. After that shutdown, only 2 instruments would be left. 2 instruments instead of 3 is the difference between partial coverage of the interstellar medium and a meaningfully complete measurement. Then came the Big Bang, which brings us to what just happened on August 4th, 2026. NASA's Jet Propulsion Laboratory confirmed the success of a procedure the team nicknamed the Big Bang. It is a clever bit of engineering that swaps 3 power-hungry thermal management devices for 3 lower power alternatives that do the same job. The swap had to happen at the same instant, not step by step, because if the heaters switched off before the replacements were fully online, the fuel lines that keep the thrusters from freezing could have begun to cool toward dangerous temperatures. If that had happened, the antenna would no longer be pointable, and the mission would have ended right there, 13 billion miles from home with no warning and no second chance. It did not end. The Big Bang worked. Voyager 2 saved roughly 10 watts of power. 10 watts sounds laughably small. It is the wattage of a small nightlight. But in the bookkeeping of a spacecraft losing a few watts every single year, 10 watts is enormous. It is enough to keep 3 science instruments running in interstellar space for at least another full year. 1 more year of direct measurements nobody else on Earth can take. If you have stayed with me this far, you are clearly someone who actually wants to understand what is happening out there. So tap that like button, drop a comment with the one question you have always wanted answered about deep space, and share this with one friend who still thinks space news is boring. The most important updates in human history are usually the quietest ones, and this one is going quiet if we do not push back. Now, what are those three instruments actually doing, and why should anyone outside a NASA clean room care? The first instrument is the magnetometer. It measures magnetic fields. Out there, beyond the sun's protective bubble there, is a magnetic field in the space between the stars. It is faint, but it is real, and it carries information about billions of years of galactic history. Dying stars across the Milky Way have been pumping plasma and magnetism out into this medium for longer than our solar system has existed. Voyager 2 is the first spacecraft ever to measure that field from inside it while drifting through it. Every reading it returns is a sample of galactic memory. The second instrument is the plasma wave subsystem. This is the one people are most excited about. And this is the one directly connected to the headline you probably saw. The plasma wave subsystem listens for oscillations in the thin, electrically charged gas that fills interstellar space. Plasma is not exotic. It is the fourth state of matter, a gas so energetic that its electrons have been stripped loose from their atoms. Most of the visible universe is plasma. The sun is plasma. The stuff between the stars is also plasma, just much, much thinner. When the plasma around Voyager 2 trembles, the way a still pond trembles when something lands in it, the instrument can pick up the vibration. And out there, far from any large object, the plasma has been quietly trembling this whole time. In recent years, scientists analyzing data from Voyager 1's plasma wave subsystem, which is identical in design to Voyager 2's, noticed something strange. There was a faint, persistent signal. A low hum, narrow and steady, sitting at roughly 3 kilohertz, that had been showing up in the data continuously since 2017 and never going away. Not a burst, not a glitch, a tone, a background frequency that the interstellar medium itself appears to be emitting. That is what the headline is really about. Voyager 2 is not picking up a message from aliens. It is not listening to a transmission from another civilization. It is hearing the faint, constant voice of the space between the stars. The plasma out there is humming, and we now have an instrument drifting through it that can hear the song. The third instrument is the cosmic ray subsystem. It counts and characterizes high-energy particles streaming into the solar system from elsewhere in the galaxy. These are particles flung out by exploding stars, by colliding neutron stars, and by other violent events across the Milky Way. Measuring them from inside interstellar space is something we have never been able to do before. I want you to feel how strange this is for a moment. We built this spacecraft before most of the people alive today were born. We sent it out beyond the planets on a path that no human being will likely follow in our lifetime. And after almost 50 years of cold, radio-quiet flight, we are still listening to it, still decoding its whispers, still learning. But to understand why those whispers matter, you have to understand the bubble of space the spacecraft just left. Our sun is not just a ball of fire. It is a star that constantly breathes. A wind of charged particles streams outward in every direction, day and night, year after year. That wind inflates a vast structure around the entire solar system, a kind of bubble called the heliosphere. Inside the bubble is solar territory, the sun's territory. All 8 planets, the asteroid belt, the Kuiper belt, everything we have ever visited or sent a probe to, sits inside this bubble. Outside of it is interstellar space, and the edge where the bubble ends is called the heliopause. The heliosphere is enormous. If you were to draw it to scale on a single sheet of paper, the planets we live on would be smaller than a single grain of dust near the center. The bubble extends roughly 120 times farther from the sun than Earth is. Voyager 1 punched through this boundary on August 25th, 2012, at about 121 astronomical units from the sun, where 1 astronomical unit is the distance from Earth to the sun, roughly 93 million miles. Voyager 2 pushed through on November 5th, 2018, at about 119 astronomical units. 2 human objects taking 2 different paths in 2 different directions out of the solar system, both reaching the same general boundary at roughly the same distance. And the bubble does something critical for life on Earth. It partially shields us from those high-energy cosmic rays I mentioned. Without this shielding, more of that radiation would reach the inner solar system. The heliosphere is not perfect armor. Galactic cosmic rays still get through in meaningful numbers, but the bubble blunts them. It softens the storm. Without it, the radiation environment of the inner solar system would be harsher than it is today, and that matters for the long-term habitability of worlds like ours. Voyager 2's instruments, floating now in interstellar space, are giving scientists their first direct measurement of how thick the shield is, how variable it is, and how it breathes as the sun's activity rises and falls over its 11-year cycle. That is not a small question. That is a question about whether worlds like ours are common or rare across the galaxy. Now I want to pause here. If you have stuck with me through the science this far, you are exactly the kind of person this channel was built for. There's a subscribe button right below this video, and I am not going to pretend that subscribing helps the algorithm. It genuinely does. Without subscribers, videos like this one, the ones that take weeks to research and days to write, simply stop getting made. So if you want more content like this, tap the button and consider turning on the notification bell so you do not miss the next one. Every new discovery from these spacecraft matters, and you're going to want to be here for it. Before we go further, I want to talk about what the data has already told us and what it has broken. Before Voyager 2 crossed the heliopause, our models of interstellar space near the sun assumed it would be cold, sparse, and quiet. One of the great assumptions of modern astrophysics. The space between the stars was supposed to be relatively calm. And then Voyager 2 crossed the boundary with a working plasma instrument, something its twin Voyager 1 did not have at the time of its crossing, and started taking direct readings. And what it found shocked the people modeling this region. The plasma just outside the heliopause, on the interstellar side, was measured at between roughly 30,000 and 50,000 Kelvin. That is not cold. That is hotter than the surface of most stars. Scientists had not predicted anything remotely like that temperature in the local interstellar medium. The models were wrong. Not slightly wrong. Dramatically, structurally wrong. The layers of the heliosphere's outer edge were different too. The termination shock, the place where the solar wind first slows from supersonic to subsonic speeds as it pushes outward, was shaped and positioned differently than the models expected. The region just inside the heliopause, called the heliosheath, turned out to have a more complex structure than anyone had drawn on paper. And the heliopause itself, instead of being a clean single line, is actually a layered, messy transition zone where properties shift across multiple distinct regions rather than changing sharply all at once. In plain English, the textbook picture of the sun's protective bubble was wrong, and it was wrong in ways that only a spacecraft positioned exactly where Voyager 2 was could have ever revealed. There is more. The two Voyagers crossed the heliopause in different directions. Voyager 1 pushed through going broadly north, out of the plane in which the planets orbit. Voyager 2 pushed through going broadly south. The fact that both crossings happened at roughly similar distances from the sun, about 120 astronomical units in two completely different directions, suggests the heliosphere is not the elongated comet shape some older models drew. It looks more spherical, or at least more symmetric than people had assumed. But the two crossings also saw different magnetic field behaviors at the boundary. Voyager 1 saw dramatic fluctuations right at the heliopause. Voyager 2 saw a calmer, smoother transition. That asymmetry is meaningful. It tells us the heliosphere is not a uniform shape. It warps differently depending on which direction you push through it. The interstellar medium itself is not uniform either. The space between the stars is full of structure we have never directly felt until now. Here's the part I find genuinely haunting. When Voyager 1 made its crossing in 2012, its plasma science instrument had already been shut down way back in 1980. The crossing was historic, but the moment was also a missed opportunity. Voyager 2's plasma instrument was still operational. So for the first time in human history, we had a working instrument at the exact moment a spacecraft crossed the heliopause, watching the plasma environment. On the other side, change in real time, measuring what came next. That moment was a gift. And the data Voyager 2 has been sending back ever since has been paying out interest on that gift for years. Every additional day that Voyager 2 keeps operating as one more point on a map humanity is drawing for the first time. We have 2 direct data points from inside the interstellar medium. That is it. 2. Out of the entire rest of the universe, we cannot yet touch directly. The next dedicated interstellar probe, if any is ever funded and built and launched, would not reach these distances for decades. So the trickle of data coming back from Voyager 2 right now, hour by hour, through that old 23-watt transmitter is genuinely irreplaceable. And I want to stop here for a second and just appreciate the engineering reality of what is happening. Voyager 2's transmitter puts out about 23 watts of power, roughly the same as a refrigerator light bulb. By the time that signal has spread out over 13 billion miles of distance and reached the giant radio dishes of NASA's deep space network on Earth, the amount of energy arriving is absurdly small. The 3 big deep space network facilities in California, Spain, and Australia have to combine their receiving power just to detect the signal at all. And when they detect it, the data rate is around 160 bits per second, roughly the speed of a dial-up internet connection in the 1990s. At 160 bits per second, transmitting a single modern digital photograph would take hours. Every byte coming back from interstellar space is precious. engineers at JPL, some of whom have been working on this mission for their entire careers, and some of whom were not even alive when the spacecraft launched, sift through every packet of data and decide what gets sent up the chain next. They decide what gets prioritized. They decide which measurement deserves to come home. And the spacecraft itself is so far away that a radio signal traveling at the speed of light takes roughly 19 hours to reach it, then 19 more hours for any reply to come back. That is nearly 2 full days of round-trip silence every time the team sends a command. They have to imagine what is happening on a craft they cannot see. Orbiting a star, they are slowly leaving, and then wait. We are in an age of impatient technology. We send a message across the planet in milliseconds. We expect our phones to know what we want before we know it ourselves, and yet a few hundred engineers in California are still exchanging letters by light, with a machine launched before most of our grandparents were middle-aged. That is worth sitting with. So where does the story go from here? JPL has confirmed that if both Voyagers stay healthy, the mission could plausibly continue operating at least one science instrument into the early 2030s. The Big Bang procedure that just worked on Voyager 2 is now planned for Voyager 1 in the coming months, which would similarly extend its operational life. Voyager 1 is more than 15 billion miles from Earth now and takes roughly 23 hours in one direction for a one-way signal. And there is one date worth marking on a calendar. On or around November 18th, 2026, Voyager 1 is expected to reach exactly 1 light day from Earth. That is the distance at which a signal from our planet takes a full 24 hours to reach the spacecraft. It will be the first human-made object in history to reach that symbolic threshold. The round trip will be 2 full days. A message, a thought, a piece of human curiosity, taking 48 hours of travel to touch the farthest reaching artifact our species has ever sent into the dark. Voyager 2 itself will not reach 1 light day until 2035, and realistic engineering estimates suggest it may not still be operating by then. But the probe has surprised every team that has ever worked on it. It has outlived every prediction. It is operating today on a fraction of the power it was designed with, on instruments with no replacement, on hardware that would have been considered museum pieces 40 years ago. If this story meant something to you, do me a small favor. Send this video to someone who loves big questions. Send it to the friend who stares at the sky at night. Send it to the kid in your life who wants to know what is really out there. Sharing is the only reason channels like this keep growing, and I would rather earn your trust through good stories than beg for clicks through fear. The universe is stranger and more interesting than the headlines let on, and the only way more people learn that is if we keep passing these discoveries forward. If you are new to this channel, please stick around. We cover the quiet, important stories like this one every week, the kind of updates that change how you see the night sky. Hit subscribe and the bell. Leave a comment with one more question, and we will see you in the next one. And let me leave you with this, because I genuinely believe it is the part most worth remembering. Voyager 2 launched before the personal computer existed. It carries a gold-plated copper record with sounds from Earth, greetings in dozens of languages, music, the cry of a baby, the brainwaves of a woman thinking about the experience of being in love. It was supposed to last 5 years. It has been listening in some form for 49. The signal coming back from it right now is real. A faint, persistent hum from the plasma that fills the space between the stars. Not a message, not a transmission, a tone, the natural voice of interstellar space itself, recorded by an instrument we built when the technology of the day was still on paper tape and slide rules. We did not fly out there. We will not fly out there for generations. But we sent something that is still working, something that is still teaching us. It is teaching us that the boundary of the sun's protective bubble is messier and more interesting than we drew it, that the interstellar medium is hotter and more structured than we predicted, that the magnetic field out there carries the memory of stars that died before our sun was born, and that if you listen carefully with patience in a 49-year-old machine, the universe will sing back. That is what Voyager 2 is picking up. That is what the headline was about, and that is why, on a quiet Tuesday in August 2026, the success of a small engineering maneuver mattered to every single one of us. Because the universe is not silent, we just had not been listening long enough, and now we are.